This dot dot indicates this the dynamic CMOS circuits, how it will look like. This dot dot indicates the static CMOS, whatever connection we used to give. If it is inverter, what is the connection in static CMOS? If it is NAND gate, NOR gate, what is the connection in static CMOS? This dot dot indicates our general static CMOS connection. In dynamic CMOS, we will have one PMOS transistor. We will have one PMOS transistor. This dot dot indicates only NMOS transistor design. Okay, only with NMOS transistor, what all the things you will do. Only with NMOS transistor, what all the things you will do. So that is about this dot dot. Now, whenever there is complement, number of NMOS transistors, number of PMOS transistors, we will use equal in number. For example, NAND gate 2 NMOS, 2 PMOS we will use. NOR gate 2 NMOS, 2 PMOS we will use. Last week we have done AB plus CD whole bar. AB plus CD whole bar, 4 NMOS, so 4 PMOS we will be using. So, but in dynamic CMOS, we will be using only one PMOS transistor. In dynamic CMOS, we will be using only one PMOS transistor. And there is a capacitor over here. And this capacitor charging and discharging will make the entire circuit operate, based on which the output is also taken over here. Output is also taken out here. If you see, this is the general structure, static CMOS general structure. PMOS transistors will be on the top and NMOS transistors will be in the bottom. In NAND gate, NOR gate, whichever design you take, in static CMOS, whichever design you take, all the PMOS transistors will be on the top, all the NMOS transistors will be in the bottom. That is about static CMOS circuit. PMOS transistors are called pull-up transistors and NMOS transistors are called pull-down transistors. PMOS are called pull-up transistors and P-down are called pull-down transistors. And equal number of NMOS and PMOS, equal number of transistors are taken. This is about static CMOS. But this will lead to noise margin and rail-to-rail output voltage, large area while fabrication, and P device, number of PMOS transistors are more in number. In order to reduce number of PMOS transistors, we are going to the next design, pseudo NMOS design. So power consumption is also high because equal number of PMOS transistors are also used in static CMOS logic. Okay, based on number of NMOS, equivalent number of PMOS are also required in static CMOS. So power consumption is high. For complex designs, it is very hectic. It is complex when the design is a big circuit. So that these are the behavior of or characteristics of static CMOS circuits. Coming to pseudo NMOS, you compare the second diagram with the first diagram. We need not use equal number of PMOS transistors. Only one PMOS transistor is enough. And we will be taking output at the same point, and we are giving ground to the gate of PMOS transistor. We are giving ground connection to the gate of PMOS transistor. Ground means logic 0. And here bubble indicates active low. So whenever you are giving 0 volt at the gate terminal, PMOS will come to on state. Whenever you are giving 0 at the gate terminal, PMOS will switch on. So this is pseudo NMOS. Complete the lower whatever NMOS transistors you are using, that will be as it is. But the equal number of PMOS not required. Only one PMOS is used in the structure. However, number of PMOS transistors are reduced. Still, we have some complex design, pull up, pull down, ratio requirement. That ratio, okay, everything we have to take care. Non-zero VOL, reduced noise margin. These are the behavior, static power dissipation. These are the behavior of pseudo NMOS transistors. Coming to dynamic, this experiment 4 is dynamic CMOS transistors. In that, what we will be doing, along with one PMOS, one more NMOS should be connected at the bottom. This is our regular NMOS structure. Above the pull down, we will use only one PMOS. Below the pull down, we will use only one NMOS. Okay. Equal number of NMOS PMOS means NMOS are called pull down, PMOS are called pull up transistor. In the second circuit, pull-up transistors are not required. Instead, only one PMOS we are using. In the dynamic CMOS, pull-up is not required. Instead, we are using one PMOS and one NMOS, and we will be giving a clock signal. Alternatively, this PMOS and NMOS will come to on state. Alternatively, this PMOS and NMOS will come to on state. Clock means 0 and 1. Alternatively, it will come. Whenever clock is 0, PMOS will be switch on. Whenever clock is 1, NMOS will be switch on. Like that, we are making the circuit to operate. We are making the circuit to operate. So by this, we are reducing the number of PMOS transistors that we can say, and a faster power saving, faster circuit due to low capacitance than static CMOS, the non-clipping output. Like that, some advantages are there in dynamic CMOS circuits. So now this is the comparison. This is dynamic CMOS, this is static CMOS, dynamic and static CMOS. In dynamic, we are using one capacitor. We are using one capacitor. In static, K number of NMOS transistors means K number of PMOS transistors should be present. NMOS are called pull-down transistors, PMOS are called pull-up transistors. So 2K transistors are required in total. 2K transistors are required in total. This is the static CMOS connection. This is the static CMOS connection. In dynamic CMOS, what we are going to do, NMOS is K in the original structure. Okay, K number of NMOS transistors in the original structure. One additional NMOS we are using, so K plus 1. One additional NMOS we are using, so K plus 1 NMOS transistors. One PMOS transistor we are using, so one PMOS. These are the total number of transistors in dynamic. Same circuit diagram. If you take inverter, NAND gate, NOR gate. If you do it in static, this is 2K transistors required. If you do it in dynamic, K plus 2 transistors are required in total. K plus 2 transistors are required in total. This is the main advantage. We are reducing number of transistors in dynamic CMOS logic compared to static CMOS. Thereby power consumption etc. can be reduced. Now this